On August 13, 2024, NIST finalized 3 cryptographic standards designed for a computer powerful enough to break today's public key security. The threat was still hypothetical, but the deadline was not. Encrypted traffic captured now could survive long enough to be decrypted later. Months earlier, Apple had already moved iMessage onto PQ3, rebuilding key establishment around post-quantum protection and repeated rekeying. Then macOS 26 widened the transition again, adding hybrid post-quantum protection to TLS, VPN connections, SSH, and developer cryptographic APIs. That should have ended one popular argument immediately. The Mac is not sitting still while the quantum threat approaches. Yet another argument has grown beside it, especially among security-focused developers, researchers, and users who distrust platform dependence. If cryptography has to be replaced across an entire digital life, who gets to decide when your machine is ready to make that change? Apple can upgrade millions of devices at once, but it also controls the boot chain, hardware interfaces, distribution path, and much of the surrounding system. Linux and BSD systems expose far more of that machinery, allowing users to inspect, replace, rebuild, or independently maintain critical components. That difference has produced a misleading claim that hardened open-source kernels are themselves the answer to post-quantum encryption. They are not. A quantum computer does not defeat RSA because the operating system kernel is proprietary, and it does not spare Linux because the source is public. Most post-quantum migration happens higher in the stack. Inside TLS, SSH, VPNs, messaging protocols, libraries, certificates, authentication systems, and key management. But the kernel still matters for a different reason. It determines how much control the owner has over the system carrying those cryptographic changes. And that is where the real confrontation begins. Not Apple versus Linux, but fixed trust versus cryptographic agility. The most dangerous quantum attack may happen years before the quantum computer exists. An adversary can copy encrypted communications today and simply wait. This strategy has a name. Harvest now, decrypt later. Its victims are not messages that matter for 5 minutes, but secrets that must survive for years. Diplomatic traffic, source code, health records, intellectual property, private archives, legal evidence, credentials, and long-lived identity keys all fit that category. A sufficiently capable quantum computer would threaten the mathematical assumptions behind RSA, Diffie-Hellman, and widely used elliptic curve systems. That does not mean every encrypted disk suddenly becomes transparent. Symmetric algorithms such as AES face a very different quantum threat. The transition is therefore more surgical and more complicated than replacing one operating system. The public key foundations have to change without breaking everything built on them. NIST's answer arrived in 2024. FIPS 203 standardized ML-Chem for establishing shared secrets. FIPS 204 standardized ML-DSA for digital signatures. FIPS 205 standardized the hash-based SLH-DSA signature system. The standards emerged after years of public analysis because replacing the cryptographic foundations of the internet with immature mathematics would be as dangerous as leaving vulnerable algorithms untouched. Shor's algorithm is the reason the public key transition cannot be postponed indefinitely. A fault-tolerant quantum computer of sufficient scale would put factoring and discrete logarithms into a fundamentally different computational regime. Such hardware does not exist today, but migration has to finish before the first practical cryptographic break, not after it. The important word is transition. Post-quantum cryptography is not a patch that can be applied to one file and forgotten. Certificates, key exchange protocols, VPN concentrators, hardware security modules, software update systems, package signing, secure boot, remote administration, browsers, messaging clients, embedded devices, backup tools, identity systems, and enterprise authentication all use cryptography differently. Some devices cannot accept larger keys. Some protocols have hard-coded algorithm identifiers. Some certificates remain valid for years. Some appliances cannot be upgraded at all. Migration begins with discovering those hidden dependencies before anyone can replace them. A machine can therefore advertise post-quantum support while still depending on classical public key algorithms somewhere else. That is why hybrid cryptography has become the practical bridge. Instead of trusting a new lattice-based algorithm alone, systems combine it with an established classical algorithm. An attacker must defeat both sides to recover the shared secret. Apple used exactly that strategy. PQ3 combined post-quantum Kyber-derived mechanisms with classical elliptic curve cryptography for iMessage, then added repeated post-quantum rekeying, so a one-time compromise would not expose an entire conversation. Apple deployed it, beginning with macOS 14.4 and corresponding releases across its other platforms. By macOS Tahoe 26, Apple's migration had moved beyond messaging. Apple's networking frameworks began advertising X255Y19ML key M768 in TLS 1.3, combining X.2.5.1.9 with the standardized MLKEM 768. Native IKEv2 VPN support gained additional MLKEM exchanges. SSH gained quantum secure key exchange, and CryptoKit exposed MLKEM and MLDSA to developers. That matters because it directly contradicts the idea that abandoning macOS is the only way to prepare for quantum attacks. Apple has become one of the most aggressive large-scale deployers of hybrid post-quantum cryptography. It also placed MLKEM and MLDSA operations behind secure enclave interfaces on supported hardware, giving developers hardware-isolated key handling for new algorithms. The proprietary question is different. Apple can document its protocols, publish research, expose APIs, release some source, and commission formal verification while still retaining control over the complete shipping platform. That control can simplify security decisions for ordinary users, while limiting how far expert users can independently alter them. Users cannot replace every security component independently or continue maintaining unsupported hardware with the same freedom available on a general-purpose open-source system. That distinction becomes clearer when looking at the kernel. macOS does not run a completely secret kernel. Its XNU kernel source is publicly released by Apple. XNU combines mock components, BSD subsystems, IOKit, and Apple-specific code. Researchers can inspect substantial portions of the kernel that actually underpins macOS. But macOS is not equivalent to a fully open Linux distribution. Many frameworks, security services, hardware interfaces, graphical components, firmware pieces, cloud integrations, and platform policies remain proprietary. The source code Apple publishes also does not give users unrestricted authority over the booted system on modern Apple hardware. Apple intentionally restricts that authority because control can itself be a security boundary. Secure boot, code signing, the signed system volume, sandboxing, system integrity protections, and secure enclave key isolation are designed to make persistent compromise more difficult. The same mechanisms that frustrate deep customization can prevent malware from replacing trusted operating system components. Open systems make the opposite trade more available. A Linux user can choose the kernel version, compile configuration, security modules, cryptographic libraries, bootloader, update source, package signing policy, file system encryption, and network stack. That flexibility becomes valuable when cryptographic standards are changing faster than hardware replacement cycles. The Linux kernel's own self-protection project describes the goal explicitly: reduce attack surface, make kernel memory harder to modify, block exploitation techniques, and build defensive mechanisms into the kernel itself. Modern distributions can combine those protections with mandatory access control, seccomp, namespaces, landlock, signed modules, kernel lockdown, measured boot, full disk encryption, and hardware-backed keys. None of that creates quantum resistance by itself. Quantum resistance enters when the protocols running on the system adopt algorithms whose security does not depend on factoring or classical discrete logarithm assumptions. The open source advantage is that those transitions can happen through components maintained by separate communities rather than one operating system vendor. OpenSSH demonstrates the difference. Years before NIST finalized MLKEM, OpenSSH had already made a hybrid streamlined NTRU prime and X.2.5.5.1.9 exchange, the default specifically to reduce harvest now decrypt later exposure. In April 2025, OpenSSH 10.0 switched its preferred default to the standardized hybrid MLKEM 6 X.2.5.5.1.9 SHA.256 exchange. That change could flow into Linux distributions, BSD systems, servers, appliances, containers, and development environments without waiting for an entirely new operating system architecture. Administrators could inspect the implementation, override algorithms, test interoperability, compile different versions, or maintain backports depending on their threat model. OpenSSL followed the same pattern from another direction. Version 3.5, released in April 2025 as a long-term support release, added MLKEM, MLDSA, and SLH-DSA. It also changed TLS preferences to include hybrid post-quantum key exchange. A huge ecosystem of software built on OpenSSL could begin experimenting with standardized PQC without changing kernels at all. This is cryptographic agility in its most practical form. The operating system does not need to predict which algorithm will remain trusted forever. It needs enough modularity that vulnerable primitives can be located, replaced, negotiated, and retired without rebuilding every application from zero. The history of cryptography makes that requirement uncomfortable. Algorithms once treated as foundational have been weakened or removed before. DES became obsolete. MD5 became unsafe for collision-sensitive uses. SHA-1 signatures were phased out. RSA key sizes grew. TLS versions were retired. Certificate rules changed. Cryptographic systems are never finished. They age. Post-quantum migration multiplies that problem because the new algorithms have different key sizes, ciphertext sizes, signature sizes, performance characteristics, and implementation risks. A protocol designed around compact elliptic curve keys may not accept much larger lattice-based material without changing packet formats, storage limits, handshake assumptions, or hardware acceleration. Network middle boxes may reject unfamiliar handshakes, smart cards may lack space, embedded processors may struggle with memory. Certificate chains can grow. Security engineering becomes a problem of compatibility as much as mathematics. Then there's the possibility that a newly standardized algorithm develops a weakness. NIST's process is designed to reduce that risk through years of public cryptanalysis, but cryptography offers no guarantee that every assumption will remain untouched forever. That is another reason hybrid deployments matter. Classical and post-quantum systems can overlap while confidence accumulates. For users looking at Linux, this makes transparency attractive. Open implementations. Let independent researchers inspect constant time behavior, memory handling, parser logic, protocol negotiation, downgrade resistance, random number use, and the exact point where keys cross trust boundaries. A reproducible package can be compared against public source. A patched library can be deployed without waiting for a vendor's next major operating system release. But transparency is not magic. Publishing code does not make it audited, and an open repository with thousands of unreviewed lines can still contain catastrophic vulnerabilities. Open source projects can be understaffed, fragmented, slow to patch, or compromised through dependencies. Users can also weaken their own systems by selecting unsafe configurations that a locked platform would never allow. The XZ-utils backdoor attempt in 2024 exposed both sides of that reality. A sophisticated supply chain compromise reached distributed open source software, yet public testing anomalies and independent investigation helped expose the malicious changes before they became a universal stable compromise. Openness created attack opportunities and detection opportunities simultaneously. Apple takes a different route. It integrates hardware, operating system security, cryptographic frameworks, update distribution, and platform policy under one authority. That can produce unusually fast deployment when Apple decides to move. PQ3 did not require each user to choose a library or configure a cipher suite. Supported iMessage conversations, upgraded automatically. The same centralization can also become dependency. If an algorithm, service, or hardware security function is only exposed through vendor-approved APIs, users inherit the vendor's migration schedule. If hardware falls out of operating system support before a future cryptographic transition is complete, owners cannot necessarily maintain the entire platform independently. This is where hardened Linux on Apple hardware becomes symbolically important. The Asahi Linux project spent years reverse engineering Apple Silicon hardware and upstreaming support into Linux. At 26, Fedora Asahi Remix 44 offered a maintained Linux environment for supported M1 and M2 Macs, demonstrating that hardware sold for a tightly integrated proprietary ecosystem could run a substantially open operating system stack. Graphics, audio, power management, virtualization, and architecture. Specific support required years of engineering, which also exposes the cost of sovereignty. Replacing the vendor stack means somebody must understand hardware the manufacturer never designed around third-party operating systems. That is not evidence that millions of Mac users are fleeing because of quantum computing. No credible data set shows a mass migration from macOS to Linux driven specifically by post-quantum fear. The real movement is smaller and more technical. Users who value ownership, long support horizons, inspectability, or independent security policy now have more realistic options than they did at the beginning of the Apple Silicon era. And those options matter because post-quantum migration is measured in years. NIST is already telling organizations to begin replacing quantum vulnerable cryptography, with a broader transition intended to remove vulnerable algorithms from approved standards by 2035 and high-risk systems moving earlier. A laptop purchased today can easily remain part of someone's data history throughout that transition. The risk is greatest where confidentiality must outlive the machine. Suppose encrypted network traffic carrying proprietary research is recorded in 2026. If its session keys were established only with a quantum vulnerable public key algorithm, the ciphertext could remain valuable to an adversary for years. The computer that created it might be recycled before the information becomes readable. Storage is cheap enough that a capable adversary does not need to know which captured stream will matter later. It can preserve vast encrypted archives, enrich them with future context, and wait for better cryptanalysis. The value of the secret can outlive the hardware that originally protected it. That is why data tomb is a useful image, only if used carefully. Quantum computing does not transform a Mac's file vault disk into a future open vault simply because file vault exists. File vault uses symmetric AES XTS encryption. and NIST does not treat properly sized AES as facing the same catastrophic quantum break as RSA or elliptic curve public key cryptography. The urgent target is the public key layer that establishes secrets, authenticates software, signs credentials, or protects session keys. Long-lived encrypted archives can also be vulnerable if their keys are wrapped or distributed using quantum-vulnerable public key systems. The threat is about cryptographic dependency chains, not one brand of disk encryption. A system can use AES-256 for the payload and still inherit future risk if the AES key is exchanged with RSA, protected by an elliptic curve scheme, or recovered through an identity infrastructure whose signatures become forgeable. A hardened operating system therefore needs two maps. The first is an attack surface map: what can execute, what has privilege, what can access keys, what can persist, and what happens after compromise. The second is a cryptographic inventory: which algorithms protect data in transit, at rest, in backups, in authentication, in signatures, and in software updates. Linux gives advanced users extraordinary control over both maps. They can reduce installed packages, disable unnecessary services, use mandatory access control, isolate applications, pin package sources, choose encrypted file systems, restrict kernel modules, and operate without mandatory cloud identity. They can also replace OpenSSL, OpenSSH, VPN tooling, TLS stacks, or certificate infrastructure as standards evolve. Yet, a poorly maintained Linux machine can be dramatically less secure than a fully updated Mac. Kernel hardening is not a substitute for patch discipline. Secure defaults, hardware root of trust, exploit mitigations, browser sandboxing, credential isolation, and rapid application updates. The strongest architecture is the one whose security properties actually survive real users. Apple's hardware integration remains formidable here. On Apple Silicon, Secure Enclave protects key material behind a separate security subsystem. Secure Boot verifies the operating system chain. The signed system volume makes unauthorized modification of protected system content detectable. File vault keys can be entangled with hardware secrets, and Apple controls the update pipeline from development to deployment. Those properties are difficult to reproduce perfectly on arbitrary PC hardware. A security-conscious user moving to Linux may gain source access while losing a tightly integrated hardware security model unless the replacement system is chosen and configured carefully. Freedom expands the space of possible defenses and possible mistakes. The post-quantum question, therefore, becomes one of sovereignty rather than automatic superiority. Can the owner identify every cryptographic dependency that matters? Can unsupported algorithms be replaced? Can trust roots be rotated? Can the system remain patched if the original vendor loses interest? Can the software be rebuilt, audited, or maintained independently? Open source platforms answer more of those questions with user-controlled mechanisms. Proprietary platforms can answer them through vendor commitment. The difference is who holds the final lever. That lever becomes especially important after official support ends. An open system can, in principle, continue receiving a new SSH implementation, a rebuilt TLS library, rotated trust anchors, and kernel fixes from communities unrelated to the original hardware vendor. Whether that actually happens depends on maintainers and hardware support, but the legal and technical path remains open in a way a fully vendor-controlled platform may not permit. That distinction becomes dangerous when cryptographic transitions involve authentication as well as encryption. Replacing key exchange protects secrecy against harvest now, decrypt later attacks, but digital signatures have a different timeline. An attacker cannot retroactively forge a signature on a communication already authenticated in the past, but future software updates, certificates, identities, and signed artifacts eventually need quantum-resistant authentication too. Apple's early PQ3 design initially retained classical authentication for precisely that reason. The Harvest Now threat applies directly to confidentiality, while forging authentication requires the quantum capability to exist at the time of attack. Later, platform APIs added MLDSA, so developers could begin preparing quantum-resistant signature workflows as well. OpenSSH shows the same staged migration. Hybrid post-quantum key exchange became default before post-quantum signatures did. By July 2026, OpenSSH 10.4 had added experimental support for a composite MLDSA44 plus ED25519 signature scheme, but it was not enabled by default. The ecosystem was moving, but deliberately. That deliberate pace is security, not hesitation. A rushed migration can create implementation bugs, downgrade paths, oversized message failures, side channels, incompatible certificates, broken hardware tokens, and operational outages. An organization that swaps algorithms without understanding where they are embedded may create a new vulnerability while believing it has solved a future one. This is why the best post-quantum architecture is not the one with the largest number of new algorithms. It is the one capable of changing algorithms repeatedly. Cryptographic agility means protocols negotiate safely, keys can be rotated, certificates can change format, libraries can be upgraded, and obsolete primitives can be disabled without destroying the surrounding system. Open source operating systems expose that machinery aggressively. Package managers can ship new cryptographic libraries, administrators can see which versions are installed, source packages reveal compile time options, configuration files expose negotiation policies, enterprise distributions can backport security fixes, independent distributions can move faster or slower according to their own risk tolerance. Apple hides more of the machinery but reduces the burden on the user. When macOS 26 enabled hybrid post-quantum TLS in recommended networking APIs, applications using those APIs could inherit the capability without every developer re-implementing a cryptographic stack. That is centralized agility, and at Apple's scale, it is enormously powerful. The catch is interoperability. Apple's own documentation notes that quantum-secure TLS protection only operates when the server on the other end supports compatible negotiation. A Mac can advertise X2 5OS49M LKE M768, but a classical-only server forces the connection back into a classical key establishment. End-to-end migration is limited by the weakest endpoint that still has to communicate. The same problem confronts Linux. Installing OpenSSL 3.5 does not magically make every website post-quantum. Running a new OpenSSH client protects the key exchange only when the server also supports the algorithm. A company can harden every workstation and still leak long-lived confidentiality through one legacy VPN concentrator sitting in a forgotten data center. Quantum readiness is therefore an infrastructure problem disguised as an operating system argument. The endpoint matters, but so do servers, identity providers, routers, certificates, backup systems, code signing keys, development pipelines, cloud APIs, and every protocol connecting them. The oldest component can determine the security of the entire path. One forgotten appliance that negotiates only classical key exchange can preserve a harvestable weak link, even while every laptop around it advertises state-of-the-art post-quantum support. For an individual Mac user, the rational choice depends less on fear of quantum computing than on the desired trust model. A supported Mac running current macOS already has meaningful post-quantum protections and strong hardware security. Switching to Linux solely because macOS supposedly lacks quantum-resistant cryptography would be based on a false premise. For a user whose goal is independent control, the calculation changes. Linux can provide a system whose kernel, cryptographic libraries, network services, and much of its user space are inspectable and replaceable. On compatible hardware, the owner can continue integrating new standards after the manufacturer's preferred lifecycle ends. For organizations, that replaceability can reduce strategic dependence. A cryptographic library can be swapped across thousands of servers without replacing hardware. An internal distribution can patch a protocol before an upstream operating system vendor exposes a high-level API. A security team can compile out legacy algorithms rather than waiting for a consumer-friendly deprecation schedule. But the organization then owns the operational burden. It must track vulnerabilities, maintain build systems, validate cryptographic modules where compliance requires it, test interoperability, manage signing keys, secure package repositories, and ensure that custom hardening does not quietly break updates. Sovereignty has a maintenance bill. There is also one final misconception hidden in the phrase hardened open source kernel. Post-quantum algorithms should not automatically be pushed into the kernel. Most application cryptography belongs in carefully maintained libraries and protocols in user space, where mistakes are easier to isolate and components can evolve without touching the operating system's most privileged code. The Linux kernel does contain cryptographic APIs for kernel-level consumers, but its own documentation emphasizes clear interfaces and leaves cryptographic agility to calling code where needed. Adding more complex cryptography to privileged code expands implementation responsibility. Hardening often means minimizing what the kernel must do, not turning it into a universal cryptographic laboratory. The kernel's job is to defend the boundaries around those secrets. Process isolation, memory permissions, privilege separation, device access, sandbox enforcement, secure boot interactions, and attack surface reduction. The protocol's job is to ensure that the secret still survives when the mathematics of public key cryptography changes. Viewed this way, Apple and hardened Linux are solving overlapping but different problems. Apple tries to make the secure choice automatic inside an integrated platform. Open systems try to make the secure choice inspectable, replaceable, and owner-controlled. Neither property guarantees the other. The quantum transition is forcing this difference into the open because cryptography has acquired an expiration date nobody can schedule precisely. No one knows when or whether a cryptographically relevant quantum computer will arrive. Estimates vary because building a useful machine requires far more than adding physical qubits. Error correction, logical qubits, gate fidelity, runtime, and engineering scale all matter. But organizations cannot wait for certainty when adversaries can store ciphertext now. The uncertainty about the date increases the value of migration planning rather than eliminating it. That is why NIST, Apple, OpenSSH, OpenSSL, governments, browser developers, network engineers, and security researchers are migrating before the machine exists. The attack may be future tense, but the vulnerable data is being created in the present. For macOS users looking toward Linux, the strongest argument is therefore not that Apple has failed at post-quantum cryptography. The evidence shows the opposite. The strongest argument is that a fully owner-controlled stack provides an escape route if the next cryptographic transition arrives after a vendor has moved on from your hardware, your workflow, or your threat model. For users staying on macOS, the strongest defense is equally clear. Stay on supported releases, use modern protocols, understand which protections are actually post-quantum, and do not confuse hardware encryption with quantum-resistant public key exchange. Apple's current platform already contains technologies specifically designed for harvest, now decrypt later threats. For users moving to Linux, the work begins after installation. Choose a maintained distribution. Keep the kernel and user space patched. Prefer modern OpenSSH and OpenSSL releases. Verify that servers negotiate hybrid key exchange. Harden privilege boundaries. Protect recovery keys. Minimize legacy algorithms. Treat source availability as an opportunity to verify, not as proof that verification happened. The future attack will not care which logo is on the laptop. It will care which mathematics protected the captured secret, which keys survived compromise, which authentication system remained trusted, and whether the software could be upgraded before old assumptions failed. That is the real reason hardened open systems are gaining attention as post-quantum migration accelerates. They offer something broader than a new cipher, the ability to keep changing the trust stack after the machine has been purchased. Apple offers a different bargain, a deeply integrated security architecture in which those changes can reach huge numbers of users with almost no configuration, but on a timeline and within boundaries controlled by Apple. The coming cryptographic era will test both models. Closed platforms will have to prove that long-term vendor control can move faster than emerging threats. Open platforms will have to prove that transparency and user control can produce coherent security instead of fragmentation. Quantum computing will not decide that argument by breaking one operating system and sparing another. It will expose whichever systems cannot replace vulnerable trust before attackers can exploit it. Post-quantum security is not ultimately about escaping macOS, choosing Linux, or worshiping an open kernel. It is about owning a system that can change its cryptography before the mathematics changes the rules.